Okay, so I'm going to film this a little out of order. So I just did my intro. Let's see here. And I want to start today's content with dealing with 2.5 further applications of right triangles, just because I've already got some stuff written on the board behind me. I want to go ahead and use that so I can use the board for other stuff in a minute here. So how can I close this? There we go. So 2.5, applications of right triangles. Further applications of right triangles. We already went over some of the stuff, how we can solve these. There are all kinds of great word problems solving right triangles. We're going to go over some more, some further applications. We're going to start off with subtended angles. These also, you may hear these called parallax angles. In fact, I'm going to insert that here. Parallax. What do you mean that's not how I spell parallax? Oh, I need two. Okay. This is the angle made when you're viewing 2 points at a distance. There are other kind of definitions, but this is a nice easy one. If you've got some points in the distance here, this is called the subtended angle. It's the angle that those two things, based on their distance apart, that's the angle they subtend. So things we use that for. Today we're going to talk about range finding mainly. Well, I guess it's one application. Surveying. Well, I guess that's really it. Those are the two main applications. So let's see. Subtense bar method. Really, I guess this could be considered either range finding or surveying technique. So, okay, so here's how this works. What we've got is this is a method for when you're viewing something, through a telescope or what have you, and at some unknown distance away. That's what we're trying to find here, is this distance. We've got a bar here, B. So we're calling it B. I don't know why your text chose all these different variables here, but whatever. So we've got this bar of known length. So when we view that bar, if we can measure the angle between these lines here, these rays, then from that we can actually create two right triangles. This top one, this bottom one, which are both identical. And from there we can use our trig functions to determine the distance here. So this is a really useful principle, but there are a couple principles I want to talk about. This first one we haven't really done a lot of, which is taking a non-right triangle here. So this is some can't remember the name of this type of triangle. We've got this triangle here with two sides of equivalent length here. But these angles are the same, but there's no 90-degree angle. What we can do is we can split this into a 90-degree angle or two 90-degree angles here to make our two separate triangles. Wow, that was complicated. But the interesting part here that I'm trying to get at is that there are a lot of times you can take just some strange triangle and you can split it up into 90-degree triangles so that you can use your trig function. Later on, when we do some more physics type applications, we'll do that. We can take all kinds of shapes and kind of divide them into right triangles, or we can find right triangles within our application. In fact, I want to say today we're going to be trying to develop some right triangles where there were previously none. So that'll be exciting. Anyway, so let's look at an example for this that will hopefully make it make sense. So find the distance where we've got our angle measured here. We've calculated that angle and we know how far apart the ends of our bar is. We've got this bar that's very accurate. 2 centimeters, that's a ridiculous bar. Let's say it's 2 meters. That's a more reasonable distance here. So this is a very accurately measured bar for whatever reason. That seems too precise for reality, but that's okay. And we want to use some trig functions here to find d. So we've got, breaking this down, so we've got our bar here that's 2 meters long, and we know our angle here, which is what? 1 minute, 1 degree, 23 minutes, 12 seconds. Okay. 1 degree, 23 minutes, and 12 seconds. Okay, so what we're going to need to do, we're going to have to come up with a right triangle here. We're going to have to determine the angle of our right triangle and at least one of the side lengths. It's easy enough to find our right triangle. Now we just need to find the angle from the side length there. And once we've done that, we're going to have to use a trig function to then find our unknown distance here, the distance to this thing. Okay, so how can we do that? Some of it's going to be really easy. So we've identified our right triangle. We've got this center line here that splits our bar into 2 equal pieces. So if our bar was 2 meters, how much is each one of those pieces? Well, they've each got to be 1 meter. All right, so let me redraw this a little bit. So what I've done is I've taken just this top triangle here and kind of redrawn that, because we only need half of this thing. We only need the right triangle, so I'm ignoring that part. That part I've shaded here. So since the whole length here was 2 meters, I know this is 1 meter. In the sheet, in your notes here, we've got that described as b over 2. If you know your bar length, you divide it by 2, and that tells you the length of your right triangle there. Okay, next up is this angle. So our original angle was 1 minute, 23 degrees, and 12 seconds. So just like the bar, we want to split that in half. You know, this angle right here is going to be half of that original angle. Okay, so let's make some room for that. I can find my eraser. There it is. And 1 degree, 23 minutes, 12 seconds. So first, what we're going to have to do is, we want, this is our original one. We want to divide that in half. Before we do that, let's go ahead and convert this to a decimal. So the way we do it, from 1.1, remember, we keep our degree here. This is going to be 1 degree. And for the minutes, in order to convert that to degrees, we need to divide by 60. So that's going to be 23 over 60. I guess I'll leave off this degree symbol. And then in order to convert seconds to degrees, we first have to divide by 60 in order to get to minutes. And then we have to divide by 60 again to get to degrees. So you can write that as either 12 divided by 60 divided by 60 again. So you could write that a few different ways. I could write that like that. So I took 12 divided by 60 and then divided by 60 again. The way I've got it written in your notes. I've got it written as 12 divided by 60 times 60. Or you could actually do that calculation first, and I would do that. 60 times 60 is 3,600. The reason I write it at 60 times 60 is I can't remember exactly I can't remember this number, 3,600, but I do know that there are 60 minutes in a degree, 60 seconds in a minute. So each degree has to have 60 minutes. Each one of those minutes has to have 60 seconds. So 1 degree is 60 times 60, 3,600 seconds. So I can't remember 3,600, but I can remember, well, it's got to be 60 times 60, and then go from there. So each of these, 23 over 60 is going to be some long, never-ending decimal here. 12 over 3,600 is the same thing. But with careful use of the calculator, you can do this all at once. So I'm going to do 1 plus open parentheses. I'll come over here and show you this as I do it. I wish I still had my calculator emulator. 1 plus open parentheses 23 divided by 60. Right? And then I need to close my parentheses. And then I do the same thing. So plus open parentheses 12 divided by 3,600. So make sure you're using your parentheses. That's why they're there. So 12 plus 3,600. Close those parentheses. And that does all of the work. All of the work for us. Okay. So we've got our angle is 1.386666, etc. Okay, so we've got our 1.386 repeating. Now, in our triangle we've got here, so this is the angle theta. Right, that was our original angle. All we did was convert it to degrees. I guess I should have my degree mark, huh? Really, I guess I need my degree marks everywhere. Okay. But this is not theta in our right triangle, where we had this full triangle. That whole thing together was theta, right? This whole angle here. Now we've got half of that, so we need to have theta over 2. So what is theta over 2? It's going to be this 1.38666666 all over 2. And just because I still don't want to erase my nice drawing down here until we actually get the chance to do it, I'll just erase this. Actually, write out a few of these. So 1.386666, dot, 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 as many decimal places as you like. So now we divide this by 2. In fact, I'll just punch it right in my calculator. So I divide it by 2, and I get so 0.693333 repeating as many places as we want. So in our triangle here, we want our theta over 2, which we now know is 0.69333 dot dot dot, just as many places as we want. So I'll say 0.693 repeating. Okay, so now we've got we got our bar length, we got this side of our triangle, we've got our angle. Once again, I'll erase the rest of my original triangle there. Now what? I was trying to find this distance here from our eye to this bar over here. So I need a trig function that relates my opposite side to my adjacent side for my known angle. And that would be tangent, right? Tangent is opposite over adjacent. I keep forgetting this degree symbol. Okay, so that's 0.693 degrees. Okay. So tangent of my angle there is my opposite side, 1 meter, divided by my adjacent side. And our variable for that we're using is d. So we'll say d. So there's all the trig part. Now you just need to do a little bit of algebra. Again, algebra, the Achilles heel of trig students. The Achilles heel of, I think, most math students. Okay. So in order to solve this for d, we need to multiply by our d on both sides. Right. Okay. And that cancels out our d there. So we've got I guess I should still be writing my bar over this angle, since we can take that 3 out as many places as we want. When I actually plug this in my calculator, I'm going to type in a bunch of extra 3's there. And we'll get to that when I actually do it. Over here, our d's canceled, but we're still left with this 1. It's not like we subtracted our 1 over d. We divided. D divided by d is 1. We're still left with this numerator 1. Okay. So now we've got our variable of interest d times this tangent of 0.693 repeating. But this tangent of 0.693, that is just a number. You know, again, tangent, you can treat all of your trig functions when you've got a trig function of a number. This is just like some other operation that you perform on this number. It's just like squaring it. You can calculate that as if it was any other operation. You know, just like you could take the square root of 0.693 or square it or cube it or whatever you like. We can perform this operation. We still just get a number out of this thing. So we're going to treat it like that. So I've got d times a number. I want to solve it for d. What do I do? The analogy here I always use is a much simpler equation involving x, because that's how everyone learned algebra. This is as if we were solving the problem 3x equals 5. So I've got my variable x, and I've got this number that's being multiplied by that I want to get rid of. What do you do there? You divide by that 3. Divide by that 3. It cancels over here, and you've got x equals 5/3. Same idea is going on here. We've got our variable times this number, so I divide by my number to get rid of it. Okay, so I've been using red for my things here, so I'll keep it up. So I'm going to divide by the number part of that tangent. Okay, and again that cancels over here. And now we're left with d equals this big old mess. Tangent of 0.693 degrees. Sorry, 1 over that tangent of 0.693 degrees. Okay. And that will be it. That's the answer we're looking for. Now we just need to do this calculation. So let me get my calculator. Now that I'm actually calculating this, like I said, I'm gonna write down a bunch more of these digits. We talked about this last week when we were dealing with significant digits. Our problem, I kept writing down 2, but our our stick here, this 2 meters, was actually a very precise stick. I don't know how we got a stick this precise, but 2.0000 meters. In reality, we probably couldn't measure that that accurately using our optics here. So it's kind of a waste of precision, but that's okay. We've got in that 2.0000, we've got 5 significant digits. We need to have 5 in our final answer. So I want to have a lot more than 5 in my calculation. I want 6 or 7. Okay, so let me do this. So I'm going to do 1 divided by tangent. Open parentheses up, or my calculator opens them for me, and then punch in 0.693333333. Just a bunch of those digits. Way too many. Better have too many than not enough, I guess. There we go. So I just punch all that in there, and then I close my parentheses. And there we go. I've got my distance is 82.6341, blah, blah, blah. But we want 5 significant digits, so I'll only write down 5 of those. 82.634 meters. We're working with meters. This is also in meters. So there we have it. I promise eventually I'll stop spending so much time on this algebra. Well, maybe I won't. You can always fast forward through the algebra parts. If you're familiar with this stuff, I mean, you're welcome to fast forward to it and get down to the trig calculations. Yeah, I'm going through all this work to preserve this picture just because I drew it kind of accurately. Drew nice straight lines for once. I didn't want to mess that up. Okay. Hopefully that's next on our list so we can be done with it. Okay. So yeah, this is going to be next. Excellent. So this is similar, I guess, to stereometric range finding. Normally, you've got little tick marks on your lens, and you, I say normally. I guess more common, is to see this being used with stadium marks. Either you've got a stick with a bunch of marks on it, and you just pick a couple of those marks and then calculate the distance there for some known angle. Or say you've got an optic on a rifle or something, or a rangefinder. You'll have little tick marks on that, and we set those tick marks in such a way that when an object is a certain height, you know how far away it is. Okay, so that's actually what we're going to do up here. We're going to look at what if we were designing some kind of optic and we wanted to put marks on it so we would know just by looking through our optic, if we could see which of the marks they lined up between. We would know if we had some idea how large the object was, how tall it was, we could then estimate how far away it was. Now this is a very common practice or it was a common practice, now we use computers for it. this was a common practice for range finding before laser methods and radar methods became more reliable and more ubiquitous. Oh, we still, in fact, I'll show you an example. I've got a great picture on here of more modern battleships, World War II, Korean War era, that we've got the nice radar on there, but we also had to use these methods because radar is still not reliable in a lot of circumstances. If you're in a noisy, I say noisy, if you're in a situation with a lot of interference from different things moving around, or like a really unsmooth surface, so like a bunch of hills and trees and things, and that will interfere with your radar, and then you have to sight, you have to do this visually. So I got a great example of that we'll get to in a minute. So anyway, without further ado, let's do this. So what we're going to do, we're going to determine the angle necessary for placement of these steady marks. Because once you know the angle, you can do it for a bunch of different telescopes. You can, okay, well, I want a telescope that is a little bit larger, has more precision. I know that I just have to make sure when I mark it, I use this angle. You can calculate these known angles. So we're going to determine that angle necessary for placement of steady marks on an optical lens used to estimate distance to a 6-foot object at 100 and 200 yards. So I've got this example. I've got it all drawn out for you. We want for when our lens is focused right here at distance 0, we want tick marks on it so that a 6-foot object, so I've got a little 6-foot guy drawn right here, I want to be able to line him up so when his head is at one of the steady marks and his feet are at the other, I know that he is 100 yards away. So this is very useful. I thought about actually showing you some sight pictures of this, but that seemed kind of maybe not a good idea. But plenty of military manuals will do that. You can look those up yourself. Okay, so you see, if we can have the same lens, we can have different marks on it, a little bit closer together, and we see when the guy lines up with those marks, we would know that he was 200 yards away. It's very useful for scouting or whatever it is you're doing for this thing. So how do we do it? Well, you see we've got two triangles. They've got one, the further one away has a smaller angle of incidence here, or whatever we're calling it, subtense. I always heard this as parallax angle. That's what we talk about it in astronomy. Okay, so it's got a smaller parallax angle or smaller subtended angle. We just need to calculate it, and the method we use is almost exactly what we did before. It's just that we're thinking about it a little bit differently, I guess. So I've got the purple guy and the purple lines up here. I've got those drawn up at the top. You can see this. Yeah. And I've got the blue guy. Again, we're looking at like a kind of average male, maybe 6 feet. That's actually not accurate. The military doesn't use 6 foot for their measurements here. I think it's more like 5'6" or something, 5'7", I don't know. So I've taken my purple triangle, my blue triangle, and I've drawn them just a little bit squished together just so I would have more room. And we're going to do essentially the same calculation we did a minute ago. So we can pick whichever one you want. I guess we could start with the purple one. I don't know, let's do the blue one. I mean, it's right here. It's closer to me. I don't have to get up. So I know this is 6 feet. I know that this is 100 yards. I'm going to have to do some conversions here to make sure I'm using the same units everywhere. But once I've done that, it should be easy to find the angle here. Okay, so let me draw my triangle. My right triangle. So notice I only drew the top part of that because the top, that makes a nice 90-degree angle. I don't need this one. This is not a right triangle. Only if we split it in half, then we get a right triangle. So when I do this, I have to make some adjustments. Now the length is only 3 feet, but it's half my original height. And this is still 100 yards. But let's go ahead and convert 100 yards. How many feet are there in a yard? There's 3. So 100 yards is 3 times 100. That's 300 feet. So we'll go ahead and write that conversion. $300 there. Wow, this is going to work out nicely. So now in order to calculate my angle, again, I want to look at the tangent function. Oh, what am I going to have to erase here? I'll just write it right here. Now I'll erase my little tick marks here. You know, these, because it's a little confusing. You know, if you've done any kind of, I guess any kind of construction. I know we get lots of construction guys. You know, we use those tick marks to mean foot. But since in here we also use them to mean minutes, I'm not going to use them. So this is 3 feet. This is 6 feet. I'll just write feet. There we go. I'll write FT. FT. I should have thought about that to start with. So those are feet. Just so we can keep track of our units. Okay, so tangent of theta is going to be, so here I've kind of defined this as theta. You can use whatever variable you want. So I've got theta here. Theta is opposite, which is 3, divided by the adjacent, which is 300. So tangent of my theta is 3 over 300. I can go ahead and reduce that. I can do it now. I can do it later. It doesn't matter. I'll just leave it alone for now. Why not? So I've got this. Tangent of theta equals 3 over 300. Now, like before, we want to take the inverse function of both sides. On the left, we're left with just our angle. And on the right, we've got that inverse tangent. Three over 300. Okay. You may also hear this. You may see inverse tangent. I guess I should wait till we talk about this in detail. You may hear this called arctan, but yeah, we'll talk about that later. I'm just going to call this tan inverse, forever. So now we've got something we can just plug into our calculator. Again, we could have simplified 3 over 300. 3, we can cancel that out of both of those or divide that out. Left with 1 over 100, but I won't. Okay, so we've got tan inverse in your calculator of 1 divided by, or sorry, 3. I'll do 3 divided by 300. It doesn't matter. 3 divided by 300. And there we get our angle, 0.57293, etc., etc., etc. Okay, so we could assume, since we're an optics company, I'm assuming we've got really precise measurements. So this is 100.0000. Actually, these are theoretical values, so this can be as accurate as we want. So I'll just round it. I don't know. We'll do 4 decimal places. So there we've got our angle, 0.5729 degrees. So very, very tiny amount there. Now, remember, that was only half of our original angle. We wanted to know the angle between our stadium marks here. So that's our theta up there. We need theta times 2 to get the actual amount. Let me draw it in the bigger version here. So we just calculated theta. The actual angle we want is this one here. It's 2 times that theta. 2 times theta there. So what is 2 times theta? I've got it on my calculator already. I can just press times 2. I get that 2 times theta is 1.146. Okay, so that is my parallax angle there. The steady angle. I don't think I've ever heard anyone call it steady angle. But now we know that no matter what optic we're making, we just have to make sure we maintain an angle of 1.46 degrees between our lenses. So in reality, we've got going on here, we don't just have one lens here. You've got somewhere in the middle of your lens, you've got the crosshairs with any stadium marks, or you've got a piece of glass or plastic film, like a circle with those stadium marks. So that would be located somewhere in the middle of your telescope. And then a little bit further back, you would have your actual lens where your eye is. So you would have to be really careful and make sure you get that angle there, matching your stadia angle. Okay, so we found our first one, 1.146. Now we do the same thing with our longer distance, and we should get a smaller angle than that, unless I've done something horribly wrong, which would be really exciting to break trigonometry. Okay, so this one hopefully will go a little bit quicker. I'll kind of speed through this one because it's very similar to the last one. I've got my triangle. Again, I'll call this one theta, although it's going to be a different measurement. We had 6 feet. We break it down. This is now 3 feet. Okay, and that's right angle. At our 200 yards, we got to convert that to feet because we're working with feet here. So 200 yards is 200 times 3 is 600. So that's going to be 600 feet there. Okay. So now when we do our tangent, we're going to be doing tangent of theta is 3 feet over 600 feet. Three feet over 600 feet. Again, you could reduce that. That's 1 over 200. And we could calculate our inverse tangent. So I'm not actually reducing it, but there's no reason you shouldn't reduce it. I just don't want you to say, well, why do you have 3 over 600 here and then 1 over 200? I'm going to just, it's not hugely necessary to do it, so I'm just going to leave it as 3 over 600. Okay, so now I calculate that. Again, my tangent inverse, 3 divided by 600. And I get that angle is 0.28647, etc., etc., etc. Just as many digits as I want there. Because the next step, remember, we need to multiply that by 2. That only gives us half of our angle. We need to know the full angle there. So it's that times 2. So 2 times theta. So this times 2 is 0.572. How do I do this? There we go. So I went ahead and rounded this up to that. Now, the exciting part here, how does that angle, and I actually rounded it a little bit before, how does this angle relate to this one? This is a fantastic thing here. There's a linear relationship. Just like 100 and 200, that's linearly related. These two are also linear. This is fantastic. This angle is half of this angle. So just what I was hoping for. I chose this. I get 0.573 times 0, or sorry, times 2. I get this one. So these things are nice. You can have a lot of stadium marks that follow this relationship, and you can have all the measurements in between marked, or you can just pick the ones you want. You may have seen optics like this, actually, that have this relationship, and it's not purely linear. So some kind of reticle there where you've got a kind of a curve with these different. So you can measure, say, the distance from the bottom to there. This isn't bad. Let me do it from what makes more sense. So you could measure from this line up to that. So you'd say, well, where does my 6-foot person fall along this line? Well, what is it? Is it do they fall at 100 yards, 200 yards, 300 yards, 400 yards, 500 yards, etc. You could just kind of extrapolate this example. We did it for 2, but you could do, you could have 5 or 6 of these tick marks, or you could have a whole line of these tick marks on in your lens there. And there are plenty of lenses drawn like that. Typically, you'll see if there are any kind of marks on your reticle there. Normally, you'll see what, 5 or 6. Okay. Yeah. So not only is this twice the distance, the angle there is half as much. So pretty cool relationship between those. All right. So now, and basically the same principle here is used with these devices called coincidence rangefinders or stereoscopic rangefinders. They're both pretty much the same principle. The mechanics of how they're done is a little different. Now, this picture is drawn where based on the lenses in here, they've got prisms that are mirrors that reflect this at 90-degree angles. So it's measuring, it's forming its right angle like this, its right triangle, and it's measuring this angle. This is the one that actually measures, but through some geometric principles, that angle is the same as this. So your device, this is very nice because this is just a mechanical device. As you adjust your lens or as you adjust the device, there are little tick marks on that, and you can see, okay, I moved it 15 degrees. Well, that means this is 15 degrees. And then you could have a table right beside you that says, okay, when this is 15 degrees and this is a known distance, I can calculate that distance using a trig function. And in fact, you can mark your little mechanical device there to actually spit out the trig function value to you. You could spit out the range directly. Okay, so some examples of this. You've got a standalone infantry device this is like the 1940s. This is the USS Alabama, which is just down the road in Mobile. And I went there with my stepson for a scout trip, which was awesome. And I took this picture because it's such a great example. I've actually got a bigger picture here somewhere. Let me see. I'll pull that up. There we go. So we can see this. They've got a couple of examples of these devices. The first one is the one that I want to point out first, because that's the really cool example where they've got a radar dish right above it. But since this is used, for in noisy situations like along the shore, there's too much junk in the way, they have to have a method of sighting distance from here as well. So that's pretty exciting that we're still using this. This was decommissioned, I want to say, after the Korean War. I don't know. And then up here we got the main battery. These are the, I'm trying to think how big these were. 13-inch? No, I think it's more than that. I think they're maybe 19-inch guns. And you see over here, and this was awesome because you can climb up inside this. Over here where these people are, there's a door you can climb up in there, and they've got this giant metal pipe taking up like half the space in there, where they've got this. You've got the two ends of your rangefinder sticking out, and there are people seated, looking down into the viewfinder, and you can sit there and look at it yourself and adjust the eyepieces, adjust that mechanical device to until it's focused, and that gives you the firing position. So fantastic stuff. In fact, let me show you some other pictures just because this is exciting. Well, to me it is. Let's see. That their targeting information was fed into these really giant mechanical computers, and for some, I unfortunately lost a lot of the pictures. This is just one tiny corner of this room. This is maybe, it's less than a quarter of the size here. Back when transistors, were large. This was largely a mechanical machine, using gears, and it's just fantastic that this is what this whole room in the heart of the ship was dedicated to solving the equations based on distance from the rangefinder and the radar when applicable from the tower there. So just amazing stuff. I've actually got a diagram of it somewhere, kind of explaining how they use that for coming up with firing solutions. It's just I was in awe, I guess, of seeing this massive computer to do something that's so simple now that your cell phone can do it. You can pull up Wolfram Alpha to solve these differential equations. Now, so let's see, what else was going to look at here? I've got a bunch more of these coincidence rangefinders, but I wanted to see. Yes. So that's a cutaway of this type of main antenna. This is the Mark 13 and the Mark 45 rangefinder. I think that there's not a Mark 45 on the USS Alabama. It's like I can't remember what it is. I just don't even remember. But you can see kind of how this worked. They've got these people here. They've got this relay down to this guy down here who sits there to direct it. Where's his eyepiece? So this is the one on top where they can see it from down here. Down in the bottom, those guys, they actually had two seats up here for people to sit and look through the viewfinder. What else did I bring in here? I guess I can just pull these up. Yeah, so those are definitely some 19-inch at least guns there. So that was massive. That's where they're firing, relying on these sight pictures, these visual measurements. Not always. I mean, clearly there's some radar. These are. So there we go. That's the one I was looking for. This is kind of an explanation of how they triangulate their positions. Getting their position fixes using radar or visual verification. And so they're constantly getting. There's a description. There we go. So they've got these gunnery computer checks. They keep feeding in their data, and the machine comes up with an approximation of the distance and how they should turn their turrets and whatnot, and comes up with a proposed firing solution. And then they feed in the actual data to the machine and see how close it was. And they do that 3 or 4 times, and you can get your actual firing solution. your approximation is good enough that it's it's essentially guaranteed. So that's for their main gun batteries there. Okay. Did anything else? No, just more of those. Oh yeah, we got to sleep in there. That was pretty awesome. Oops. These are all more historical ones. These have to do more with other types of. Yeah, this was. I was trying to talk about this. We're talking about the. What do you call this thing? It's escaping me. Well, whatever. You've got this thing for measuring your distance up to some known star. So this is an ancient one. I say ancient. 1573. That's not so bad. That's not so old. More of a modern rangefinder using lasers. Is there anything up here? Yeah, these are just I believe these are just well, I take that back. Those do look like these are potentially more of the rangefinders on the edge of the guns there. So there we go. There's another nice example. This is again the radar, and then right below it we've got the two things sticking out, so you can view you've got your lenses on different sides to do this same kind of coincidence range finding. So yeah, sorry, I'm just I'm just going through this for fun, give you some nice examples, because this is what I do when I'm out about on these scout trips and whatnot. I have a great time looking at this stuff. Oh, there you go. So there's our picture, right? There's kind of their explanation for it. Oh, and it has their stuff. They've got the Mark 48 optical rangefinder. Okay. Oh, actually, they've got a few of them. The Mark 13 is the one on the front. The Mark 8 is the one in the aft and back. Oh, so that would be the one on the. Oh, that was the one we just looked at. We just looked at the Mark 8. The Mark 13 was the one on the front of the ship. Yeah. And the Mark 48, that was the one. That's the one up in the tower, I believe. Okay. Not that that's hugely interesting to anyone other than me, but there you go. Sorry. I hope you can skip through this trivia part. Okay, now on to the last thing. Again, this is kind of related to military type things, and this should actually be pretty easy, these problems. This is just an introduction to this, mainly to get you used to this idea of bearing. Bearing can be talked about in a few different ways. It's either they give you just one angle, so you say my bearing is 32 degrees. That means measuring from north, going in a clockwise direction, you've gone 32 degrees. So this arrow here on the right, that is the direction we're talking about. So if you want to go in that direction, you'd say, okay, I'm going in a bearing of 32 degrees. And a lot of other examples, 164 is almost straight down. 180 would be straight down. And you can go, all the way around the circle up to 360 degrees. But you would say, I think, bearing of 0. You could say bearing of 360 degrees. I'm sure no one would care. I don't know. The second method is to either first indicate from north, or measuring from north, or we're measuring from south, and then you measure the direction that you're going in. So like I could say, these are all kind of out of order, but whatever. The first one, I could say north 42 east. It means starting from north and going in the eastern direction, or going clockwise. I got a mirror image here, don't I? Going in the eastern direction, then you've got north 42 east. I'm trying to figure out my camera here. Yeah, I have to go this way to match what's on the screen. That's weird. Conversely, if you skip all the way to the end here, we've got north, and now we want to go in the western direction. So we would say north 52 degrees west to mean that we're going in the western direction. Same thing, you can measure from south. You can measure from south in the eastern direction, or you can measure south in the west direction. So we've got south 31 east, we're going east. South 40 west, we're going west. So I did a lot of orienteering when I was younger, in scouts, and also with this forestry company, which was just an awful job. I remember out in the woods, you know, with your compass, and just sweating, it's real pain, and you're trying to figure this stuff out on your map. You're like, okay, you know, go 32 degrees, whatever direction. Or the boss tells you, okay, I want you to paint this line at 42 degrees, 30 minutes. You're trying to do all that with a paintbrush in your hand and a machete. Anyway, I don't even know why I'm going off about this. Actually doing this, and that part's pretty easy. The problems we have look confusing, but they're really not, because this is something that could be kind of cool later on when we deal with non-right triangles, but we don't really deal with those until like chapter 7. So we got plenty of time for that. So all of these complicated looking examples really boil down to find the 90-degree angle. Like, I looked through all the examples in the text, and they basically give you a 90-degree angle. So I'm going to walk you through this one so you can see what I'm talking about. Okay, marker. A ship leaves port and sails on a bearing of north 47 degrees east. So we got our ship. We're going north 42 degrees east. Actually, before I do this, I'm going to go ahead and write my rows over here in the corner, in case you don't know. North, south, west, east. You need to know your cardinal directions. I guess, you know, old school maps. I guess all maps still, you know, have a rose or just north indicated, and you should know which directions the other ones are. So from our port, we're going to call this our port. We go north 47 east. So there's the northern direction, and we're going to go in the eastern direction. 47 degrees, so the whole thing's 90 degrees, right? All of these are right triangles. These are all right angles, 90-degree angles. Okay, so that's a 90-degree angle. 47 is just a little past halfway. So something like that. I'm going to draw this pretty big. So we've got let's draw even bigger. We've been chugging along on our boat there for 3.5 hours. Okay? It then turns and sails on a bearing of south 43 degrees east. So there's the south direction. East is that way. Let's see. So we're going south 43 degrees east. So again, 45 is right there. You know, it's cutting that in the middle. 43 is just going to be a little bit less than that. So we're not going all the way to 45. We're only going 43 degrees. So it's more like this. Okay. And how far are we doing that for? We're doing that for 4 hours. Okay. So say it's like that. And then they ask us, how far is this thing from port? So there's our port. That's just a terrible drawing. So the question is, how far have we gone there? What is that distance? And so in order to do that, we've got a triangle. We need to find a right triangle in here that we can actually work with. In our case, it's going to be pretty simple. Now, let me do something. So I've got my north, south, everything. I'm gonna erase my east and east lines here, because now that we've got that, we're good. Really, I can erase the whole thing, but I want to use this north-south line to kind of demonstrate something. And this is just how I do it, you know, when I solve this thing. I actually left my east lines up there, but I got a little confused and realized, oh, I don't need those. So these are my really terrible north-south lines. Now, these are parallel, you know, right? If this one's going north, this one's going north. I mean, they're parallel lines. You have to remember some stuff from your high school geometry class. I know you got to think way back about how these angles relate. When you've got a line that crosses, and this is the only line I'm really interested in, this first one to start with. When you've got a line that crosses these parallel lines, we know some stuff about the angles here. So this was the angle they gave us first. This was 47 degrees. What does that tell me about these angles over here? Again, where this first line crossed, right? It tells me that this is 47 degrees, although I don't need that, right? This is 47, this one's also 47. More importantly, this one is 47. That's the one I actually need. Why do I need it? Well, because they told us this angle was what? This angle was 43. That's where we took our second bearing from. We turned south 43 degrees east. So that was our second angle there. 43 degrees. So we got 47 plus 43. That's 90. So that's why we care there. So we kind of scratch out my line that I don't need. So my 47 plus my 43. That gives me my 90-degree angle up in this corner. Okay. So now that I've got this is a simple problem. I've got my right triangle where this is the 90-degree angle, meaning this is the hypotenuse. So what do I know about right triangles? If I've got these two sides, I know that they have to be related to this side using the Pythagorean theorem. Okay. So our two legs, so we've got this triangle here. Where this is 90 degrees. that doesn't look like 90 degrees, does it? We've got that, and we know, typically we would call these what, A, B, and C. We can use the Pythagorean theorem to find C. That's our hypotenuse here. So how do we do that? Well, we could do it with hours, but that would be weird. What we need to do is pull this last piece of information from our problem that had to do with the speed of the ship. So we know how far it was going along these. I never did bother to do this calculation, but I guess we should do it. And now is as good a time as any. We've got how long it traveled. We have the rate it traveled at. We need to figure out the distance from that. Fortunately, we have a really handy formula for that. Distance equals rate times time. So this first leg of the journey, we know our rate. Well, our rate's the same the whole time. It's 22 knots or nautical miles per hour. And how long did we do that for? We did it for 3.5 hours. And that gives me my distance for this first leg of the journey. So we've got our 77, and this was in nautical miles per hour. So this is 77 nautical miles, which are also called knots, I think. So that's weird. Okay, so in Let me clean this mess up. There we go. We've got, or we determined that was 90 degrees. We've got our distance here is now 77. The distance here where we had 40, we had 4 hours, 4.0 hours. So that's, again, we can do the same calculation. Distance equals 22, our rate, times the amount of time we spend, 4 hours. And 22 times 4 is 88. Okay, so this leg of the journey, we've gone 88 miles. Okay, so from that, how do we figure out the last leg? Again, we use that Pythagorean theorem. A squared here plus b squared has to equal our unknown side squared. Okay. So we'll do 77 squared plus 88 squared has to equal our unknown side squared. We just need to calculate that. 77 squared plus 88 squared. In order to solve this for our variable, we just need to take the square root of both sides. And I can do that. I'll just do it right here. Okay, and that leaves me with just my unknown distance there. Is equal to whatever this is. Now make sure you can put this in your calculator correctly. When I do that, let's see, 77 squared plus 88 squared, close my parentheses, and I get 116.93, again, nautical miles. Now, since this, we only had 2 significant digits, in reality, we should round this to 120. In order to keep just 2 significant digits. I've already told you I'm not hugely concerned with significant digits, so just follow. MyLabs Plus should just tell you usually, round this to 2 places. If it doesn't, do your best and let me know if there's a problem on a quiz or a test. On your homework, you can just redo the problem and make sure you're paying attention to the significant digits on the problem. So if your answer was wrong, it was just a rounding error, you can knock out. You can do this one last calculation. If you click View Similar Problem, it'll give you another one, and you can just plug in your new numbers. Well, I guess you need to find your distance and your distances again. But okay. So these problems are super straightforward in your book because they're all like this. There's a 90-degree angle in there. If you draw this picture, it should be obvious. As long as you're thinking, okay, that's about halfway, that's about 45 degrees, that's 45 degrees. Which one of these looks like a right angle? That's probably not the best way to do it. But drawing these parallel lines, the north-south lines, and remembering those rules from your geometry should get you through it. In fact, let me see here. Your book does have this as part of 1.1. I'm going to post the links to section 1.1, so you can review that in there as well. I think it's 1.1. Oh no, they're in section 1.2, page 11. There's a table of those relationships if you want to brush up on your geometry. If you've got that line intersecting 2 parallel lines. So that's on page 11 of your text. Okay.